So where we left off last time was discussing the Java thread lifecycle. And if you recall, we had talked about what the thread lifecycle is and the various states that you have with threads. And I described some of the steps involved in starting a Java thread. The key point of that discussion really was to alert you to the fact that creating a thread is a non-trivial operation, so use it only when it makes sense. And what we're going to do today is we're going to talk about various ways to stop Java threads. And this should be very helpful for the current assignment because there's lots of things in there that require knowing when to stop stuff. And we'll start by discussing how to stop a thread with a volatile flag, which is honestly not the best way to do it, but it's worth knowing about it. And then we'll talk about better ways to do that. Okay, so why would we want to stop a thread in the first place? Well, there's a bunch of different reasons. One reason might be that an operation has been running for a long time and the user's getting bored or tired of waiting for it to complete. So you might be doing something with a user interface and for whatever reason it's taking longer than you expect, and so you're like, heck, I'm out of here, I want to go and do something else. I'm bored waiting for my computer to finish. And that doesn't happen as much as it used to because internet's gotten faster, but it's just a good thing to know how to cancel stuff when you don't want it to run anymore. Another reason might be if you're programming an Android and you have an activity that's destroyed, stopped, or paused. Maybe you press the back button or there's been a runtime configuration change. And so in that case, you want to cancel a thread that's running in the background because the context in which it's running is no longer going to be valid when it finishes. So you want to cancel it so it doesn't give you some nonsensical result when it's all done. Another reason for canceling things might be you want to cancel other operations once you've got a result. So this is what's sometimes called speculative computation. So you might spawn a whole bunch of threads to look for something in different data sets or different databases. You might have a sharding-like model, kind of like Google search. And once one of the threads has found the answer, you say, all right, everybody else stop running because I don't need anything more. A good example of this is the invoke any method that's available on the Java executor service. And what invoke any does is it waits for the first result to come back because it's going to take any result, and then it shuts the other ones down. Well, interestingly enough, stopping Java threads is surprisingly hard. And I sometimes refer to this as the sorcerer's apprentice problem. Anybody here ever see the famous Disney movie from Fantasia? You ever see Fantasia? And there's a classic clip in there called The Sorcerer's Apprentice, which is about Mickey Mouse, who's basically he's the apprentice to the sorcerer. I relate him sort of to a grad student, maybe. And the wizard, the sorcerer, has said, I want you to fill up this, take water from the well and do something with it. And Mickey gets clever, so he decides he's going to make the broom do the work. But then the broom doesn't stop, so he chops the broom up into pieces. So now we've got like hundreds of brooms all carrying the water, and he can't stop the brooms. They're going on, and he's drowning. Well, that's the sorcerer's apprentice problem with respect to threads. Threads are sometimes easy to create, but hard to shut down. Interestingly enough, there is no safe way to stop a Java thread involuntarily. You can stop a Java thread, but you can't stop it. I mean, you can stop it by shutting the program down, but that's not a safe way because that means that the state may not get cleaned up properly. So there was a method at one point called stop, and that's been deprecated because it's inherently unsafe. If you want to read about why that's the case, take a look at this link. So you can't use the stop method in any way, shape, or form that's safe, and that's because when you stop a thread, it could be in the middle of doing something. It could have allocated a bunch of resources, and when you stop it, those resources won't get cleaned up. So that's the reason why you can't stop a thread safely. Here's some of the things that happens. All the locked monitors are unlocked as the exception propagates up the stack, and therefore any objects that are protected by these monitors can be left in an inconsistent state. So just bad things will happen if you try to stop a Java thread by using stop, which is deprecated. So therefore, we have to write our threads in a way that they voluntarily check to see if someone has asked them to stop. So it's called voluntary thread termination, not involuntary thread termination. And so basically the big picture view is, while you're running, you have to periodically check to see if you should stop. So there's methods, we'll say in a second, that can be used to do this. There are two ways to stop a Java thread voluntarily. One way, which is what we're going to look at first, is to use a so-called volatile flag. So we'll take a look and see how this works. And it's got to be marked as volatile. If you recall, what does volatile mean? Anyone remember what volatile means? That's right. So what it means is that the value of this field, which in this case is a Boolean, but could be whatever, this value will not be cached in the processor or multi-core processor cache. Instead, it'll be written and read atomically back to main memory for every read and write. We'll talk more about this in a second. The other way to do it is to use so-called Java thread interrupt requests. And the key to remember here is requests. So you're requesting a thread to stop. You're not forcing it to stop. So let's first start by talking about how to stop Java threads using a flag. So here's kind of the way to do it. So we're going to define, we're going to have code that looks kind of like this. We're going to have some class that implements runnable. Of course, this could also be a Lambda expression, perhaps. But the bottom line here is we're going to have a run method, which is going to keep running, and it's only going to stop when this flag m is stopped is set to true. Here's what it looks like. We're going to define a m is stopped field, which is volatile. And the reason we use volatile, as we just talked about, is that makes sure that reads and writes go directly to memory, bypassing the processor cache, so that they're always going to be handled atomically by the memory system. And whenever we want to stop the thread, we're going to call a method, which is called stopMe, which is going to set m is stopped to true. Notice it started out as being false. And that's going to essentially define a data-centric critical section. It's kind of a funny term, but essentially reading and writing to m is stopped is atomic. So it's sort of like a critical section you can assign true and false to in this case. And then down here, as we saw before, we'll just check this periodically. Now, you have to decide sort of how often you're going to make this check. Are you going to check every time through the loop? Are you going to check every 100 times through the loop? That may be something you want to do. If you check it every time, it could get expensive. Once you're sure that you've been stopped, once the flag has been set, then you simply return. And I'm sure you all remember that returning from a run method in the thread causes it to go away and shut down. This solution is very lightweight. So there's hardly any overhead with respect to the mechanism involved. The mechanism is trivial. You're just reading and writing to a field atomically. The downside is, you may end up spinning, which could be a problem, but we'll come back to that later. The real issue, though, is this is not integrated into the Java execution environment. So the virtual machine, the runtime environment doesn't care about this thing. So if there's any methods that block for any reason, they're not going to be able to be interrupted. So if you try to do some kind of a read operation, or you try to wait on a semaphore, or basically anything that's a blocking operation, those blocking operations don't know anything about your m is stopped flag. So despite the fact that a thread has set it, the thread that's blocked doesn't care that this has happened. So as a result, it may be very non-responsive. So the shutdown processing may take a long time, which is why I show the picture of Rip Van Winkle, right? It could take a long time. You could grow a long beard by the time you're actually in a position to be aware that you're shut down, because you could have been blocked for a long time waiting for some other thing to happen. Okay, so bottom line, using a volatile flag is very lightweight. There are situations where it comes in handy, especially for purely compute-bound operations, but it's not an appropriate mechanism if you have blocking operations, which might be the case for more sophisticated concurrent applications that do I/O or wait on various synchronizers and so on. So the next part of our discussion will focus on, for my money, the most interesting aspects of trying to shut down threads. And that has to do with stopping them via an interrupt request. And we'll talk about the differences between Java thread interrupts and more traditional operating system or hardware interrupts. They both use the word interrupt, but they're not really the same semantically. And we'll also talk a bit about patterns of interrupting Java threads. And this will be helpful because your assignment number 4 deals with some of these patterns. So learning how to use them correctly is important. So we talked earlier about how to stop something with a volatile flag, but I mentioned it was sort of unsatisfying because the execution environment knows nothing about how to do this. So an alternative way to do that is by calling a thread's interrupt method. So there's a method that's available on thread. And what this does is it posts an interrupt request to the thread. And these interrupts are implemented internally using something called the interrupt status flag, which is basically a flag that the Java thread implementation knows about and other parts of the Java virtual machine and other parts of the Java class libraries know about. So they all have to work together in a collaborative way. The way you set this flag is by calling the interrupt method on thread. So if you say interrupt, that will set the flag. And programs can then check this flag using 2 different methods. And these methods are very subtle because they have nearly the same name and similar semantics, but not exactly the same semantics. So you have to be aware of the behaviors and how they work. And you'll see that they have somewhat different side effects on the interrupt status indicator, which is part of the thread implementation. So one of the methods is interrupted, and that tests whether the current thread has been interrupted and is interrupted. If you read the thing, it says, test whether this thread has been interrupted. So they sound like they're doing exactly the same thing, but they're actually not doing exactly the same thing. That's one aspect. Another aspect is that interrupted is a static method, which means you can say thread.interrupted, and it's a static call, whereas isInterrupted is a non-static method, so you have to have a thread instance in order to call isInterrupted on. And you'll see the main issue has to do here is whether they affect the interrupt status flag. Interrupted does affect that flag, whereas isInterrupted does not. It just checks to see whether the flag has been set. Kind of bizarre. If I designed Java, I probably wouldn't have come up with these names that are so close in spelling but have different semantics. So here's a very simple program that illustrates how we could use this. And what it's going to do is we're going to have a main function, as always. Inside the main function, we're going to make ourselves a new thread. We're going to start that thread. And so that thread, which will run this code here, will run concurrently with the main thread. And let's assume, for sake of argument, the main thread does something useful. I just put ... here. And at some point, we're going to go ahead and interrupt it. But between the point where we start it and we interrupt it, this background thread is going to do some stuff. And as you can see here, what it's going to do is it's going to loop, and it's going to do some processing that blocks, and it's going to do some processing that doesn't block. And we'll see that each of those methods have to be handling thread interrupts in a slightly different way. So let's assume, for sake of argument, the background thread is off doing its thing. At some point, the main thread says interrupt the background thread. You can see it does that by saying T1, which is the thread ID, or sorry, the thread object, T1.interrupt. So that goes ahead and says, please consider shutting yourself down. And the 2 methods, the process blocking and process non-blocking, inside that background thread have to be implemented in a way to voluntarily check to see if an interrupt occurs. So let's take a look at process blocking first. So what does it mean to be blocking? It means we could call methods like wait. You recall wait. You're doing wait in your current assignment. We could call sleep. You might recall sleep. Sleep puts you to sleep for a while. And what happens here is sleep and wait and join. There's a bunch of these so-called blocking operations, as well as blocking I/O calls on so-called interruptible channels. All of these things are implemented in such a way that they internally check to see if the thread has been interrupted. And if the thread has been interrupted, then these blocking calls are programmed to wake up, and they will throw the interrupted exception. So in that case, if these calls are interrupted, the interrupted exception will be called, and you'll have to deal with it somehow. And there's various ways to deal with it, as we'll talk about shortly, the various patterns for how to deal with the interrupted exception. So that's the blocking version. Here's the non-blocking version. Remember, with non-blocking, we're not calling methods like sleep or wait or join or blocking I/O calls on interruptible channels. We're just doing something that's compute-bound. And so as a result, we need to program our compute-bound code that we write to periodically check to see if, in fact, we've been interrupted. And if we have been interrupted, then we're going to do something. In this case, we're going to throw the interrupted exception. So you've got to explicitly make that check. And so one way to do this is to call thread.interrupt. Remember, that's the static method. When you call thread.interrupt, if the thread has been interrupted, it'll return true, and it'll also clear the interrupted status of the thread. So the thread is no longer marked as being interrupted. That's important to remember for some use cases. In fact, we talked about that when we were showing some of the stuff. You may have to reset the flag, as you did in some of the acquire uninterruptibly methods you've implemented recently. In this particular case, we're throwing an interrupted exception. You could obviously throw other exceptions too if you wanted to, but that's a sensible one in this case. Note that a Java exception is allocated and treated just like a normal object. So it's going to be allocated off the runtime heap, and it'll be passed up, and you can catch it and do various things to it. The other method is interrupted. Now, in this case, notice that we had to get a thread object, which we're going to hopefully define in a syntactically correct way. This is not syntactically correct. It's a final thread, my thread. And what we're going to do here is we're going to say my thread.isInterrupted. And what this is going to do is it's going to return true if an interrupt has happened, but it's not going to clear the interrupted flag. So you can actually call this multiple times without affecting the interrupt status of that flag. That's not as common an approach. It's much more common to use the thread.interrupted method and then just keep track of whatever you need to do if you need to reset the interrupted flag later. Now here's a little bit of trivia. This is really, really dark and mysterious trivia, but you can actually override these methods. So you can override interrupt and isInterrupted. And I've actually written programs, not for the current case of what you're doing for the class, but I've actually written versions of the Palantir simulator stuff where we actually overrode the interrupt and isInterrupted methods from something that extended thread, being thread in this case, and did something different in them. And there were various reasons for doing that, which we didn't have to worry about for the way that we did it this time. So it is possible to do this. However, you need to be very, very, very careful when you do this. Take a look at this Stack Overflow article for discussions about how to do it. But you really, really, really have to know what you're doing. It's kind of getting yourself into big trouble if you don't. So let's talk a bit about how to stop Java threads in a relatively robust way. So as always, whenever you start finding complex pieces of software, you discover that there's usually patterns for telling you how to do it effectively. And this is particularly true for Java, stopping Java threads, because it's not the kind of thing that the language and the runtime system really does in a sensible way for you. You have to think through some of the use cases. So there's a bunch of different patterns for doing it. And if you take a look at this article, they describe all the different patterns we're about to talk about. So one approach, which is something that we actually just talked about in the frequently made mistakes for assignment 3B, is to simply propagate the interrupted exception to the caller or callers by not catching it. That's the easiest thing to do. That's basically punting, right? So you're going to say, like, I don't know what the heck to do, but whoever called me is going to have to figure it out. So here's a simple example. We might have a string blocking queue, which is going to have a blocking queue, and we're going to have put and take methods. And you can see here that both of these things throw interrupted exceptions. And so all we do is we simply forward the calls to put and take onto the blocking queue that we've got here. And if put or take happens to be interrupted, they're just going to take the exceptions that they throw, and they'll be propagated up to the caller, and we'll make it the caller's problem to figure out what to do about that. So that's kind of, it's kind of honestly a bit of a punt, but it's a time-honored way of handling things. And that's pretty much the way that you should be thinking about implementing your acquire method on a semaphore if an exception is thrown, because you just basically let it propagate to the caller, make it their problem. And the way this is done, as I just mentioned, is we put the interrupted exceptions in the signature. We declare the throw spec in the signature of the method. If we were to remove these throw specs here, then this code wouldn't compile unless we did something to catch the exception inside the method. Another thing you can do is you can perform task-specific cleanup before rethrowing the exception. So, you might come in, wait on a lock. If an interrupt occurs, then we're going to go ahead and clean up the resource. We're going to remove the lock and do some stuff, et cetera, and then we're going to rethrow the exception. So this is a good example of catching an exception, cleaning things up, and then rethrowing it. So it's still propagated to the caller, but we did some cleanup between the point where we discovered the exception occurred and where we threw it. So that's a very common thing to have to do if you've got resources that were allocated that you don't want to leak or that need to be put into a particular state in order to preserve certain invariants. And this is often called the Hippocratic oath of exception handling. The first thing to do is do no harm. And if exception is thrown, don't do any harm. Don't blow up. Don't leak resources. If this was a C++ class, we talk a lot more about how to handle exceptions by various types of guarantees. There's sort of weak guarantees, there's strong guarantees, there's no-throw guarantees, and so on. And Java can be used in much the same way. Yet another thing to do, which you've also got experience with at this point, is to restore the interrupted status after catching the interrupted exception. So here's a simple example. We're going to have a thread or a runnable that's going to loop, and it's going to wait up to a certain amount of time to get an item off of a queue. And if it gets interrupted, then we're going to reset the interrupt flag so that the caller knows that something happened. And the basic reason for doing this is to preserve evidence that the exception occurred for higher levels in the call stack. And you guys also did that too. If you recall the acquire uninterruptibly method, you did this in order to keep track of the fact that an interrupt occurred, even if you ignored it for the duration of the acquire. You still want to let the caller know, hey, there was an interrupt. You might want to deal with it somehow. And then the final way to do things, which is really an anti-pattern, is to simply handle the interrupt and swallow it. So in this case, this is the same kind of thing we did before. We're going to get the interrupt and basically swallow it. As a general rule of thumb, reusable library code should never swallow interrupt requests, because it's usually important to somebody that an interrupt occurred, and you don't want to just make it go away, because chances are that'll cause you problems down the road. Okay, so those are some patterns. What we just discussed are sort of 3 patterns and 1 anti-pattern, arguably for handling interrupts, and you've dealt with all those kinds of things. And you'll notice, by the way, whenever you put try catches around your code and do nothing, I always yell at you and say, don't do that, right? You're swallowing the interrupt, and that's why. Let's talk now about the different types of interrupts that you may be encountered. If you take an operating system class, you'll probably learn that interrupts can occur at the operating system layer. For example, in Unix and POSIX platforms, and even to some extent in Windows, you have something called a signal, which is basically an interrupt. If you take a computer organization class, then hopefully they'll teach you about hardware interrupts, which is something that's actually handled by the hardware devices. They interrupt. That's how they communicate with each other at a very low level. And these types of interrupts, the hardware interrupts and the operating system interrupts, generally are asynchronous. And so what that means is they can occur at sort of any point in time. Logically, there may be low-level points in time where interrupts are masked by the operating system or the hardware, but they can essentially occur asynchronously. And they're also typically independent of the instruction that's currently running. So the interrupt is occurring sort of out of band as opposed to in band. So that's when an asynchronous interrupt occurs. And as a result, for asynchronous interrupts, the program typically doesn't test for them explicitly. You don't have a call that says, if asynchronous interrupt occurred, then do this, because they occur out of band. So as a result, you'll typically have an interrupt handler, like a signal handler or a method that gets called back, some kind of handler that you'd have to handle the interrupt. And that's done. It's actually very complicated to program like that because things are occurring at different levels of abstraction, and it's tricky. So another model is another property of interrupts at the operating system or hardware level is they're typically preemptive. And what that means is that they will pause and then later resume the current flow of execution of whatever code is running without getting its permission. They just sort of say, okay, I'm going to go ahead and pause what's happening, going to run something else. When that other thing is done, I'll let the thing that was paused continue. And this is typically done, this is sort of an implementation detail discussion, but usually it's done by creating a new activation record and then running the interrupt handler, the signal handler, on top of the current stack. So it basically pins the computation it's running at the moment, and it shoves a new activation record on top of the stack, does whatever is in that activation record. When the activation record returns, then the code underneath it just continues to run. So that's usually the implementation mechanism they used for that. Here's a real simple example showing how a program might catch the SIGINT signal for Unix. SIGINT is something you can use to tell a program you want to interrupt it. So if you have a program that's running, then you can typically hit Control-C, and that will interrupt the program. And this occurs asynchronously. It preempts the current instruction, and it isn't tested for explicitly, typically. So here's what it might look like. You have a main program in C. You set your signal handler, which is this piece of code up here, to handle the SIGINT interrupt or signal. And then you go here and you sort of wait for 10 seconds in a loop over and over again. And if somebody types Control-C on the command line, then that will cause the current thread to be pinned. This signal handler will run. In this case, it just checks to see what happened, and it prints something out. It turns out that asynchronous and preemptive interrupt handling make it really, really hard to reason about your program. And you can find out more about that here. If you take a look at this Wikipedia article about Unix signals, it talks about some of the risks. It's really complicated. Here's a couple of examples of the typical problems. You can have race conditions that occur because you might not have the programs locked properly when the interrupt handler runs. The locks may not be held properly. You may also have something called reentrancy problems, and that's because the function that was interrupted might be in the middle of doing something important, like putting something into a linked list, and the linked list may be in some inconsistent state. And when the interrupt handler runs, if it tries to do something that required the linked list to be in the right state, the list would be in an inconsistent state because it was sort of pinned unexpectedly by the interrupt handler, the signal handler, and causes all kinds of headaches and problems. That's why signal handlers in Unix typically can do something about as powerful as setting a flag, and that's about all they can do. There are other things they can do, but that's the typical thing you should be allowing them to do. Another problem are non-transparent restarts. So if you're in the middle of an I/O operation and you get interrupted, you may have to explicitly restart the operation when the call comes back. So that makes your code a bit more tricky to write and to reason about. Again, take a look at some of the articles here about what goes wrong. So because of all these complexities that arise with asynchronous and preemptive interrupt handling, Java does it a different way. So Java's threads interrupt mechanism differs from the hardware and operating system interrupts. In particular, delivery of Java thread interrupts is synchronous and non-preemptive rather than being asynchronous and preemptive. So in particular, Java thread interrupts do not occur at some arbitrary point. They're done in a very controlled way, so they're synchronously checked as opposed to asynchronously occurring. And they don't arbitrarily pause and later resume the running code. You have to explicitly write your code to know how to deal with the interrupts, to recognize that they occurred and to deal with them. And therefore, as a result of all this, the programs have to explicitly test for them. And they do it like this, like we just talked about. So you have some code, you check in the loop somewhere, did an interrupt occur? If so, you do something about it. But your code will not be interrupted asynchronously or preemptively. You have to synchronously check, and if you need to preempt something, you have to do it because it's non-preemptive. A very common thing to do is to handle stuff and then throw the interrupted exception to the higher layers in the stack, which then do their thing accordingly. Now here's something else that's like really, really annoying and bizarre. Certain operations in Java cannot be interrupted, which is just maddeningly crazy. In particular, blocking I/O calls that aren't made on interruptible channels. And here's a good example. This is a very, very simple example. Here's an example where we have a run method on a thread, which is going to sleep, and it's going to basically read. It's going to say system.in.read, which is going to block. And you cannot get that thread to shut down come hell or high water, which is bizarre. That's why they later added something called Java NIO, or new I/O, which had interruptible channels. So you can do I/O operations that can, in fact, be interrupted. But they never went back and really fixed the older stuff for some strange reason. OK, so here are sort of some parting thoughts about thread interrupts. They are a portable way to stop Java threads, but they require cooperation. In particular, threads have to check periodically to see if they've been told to stop. The thread interrupt mechanism is very fragile because all the parts of a program have to be coded to do this checking using those patterns we talked about, which is tedious and error-prone, not surprisingly. But that's the way it's done. So if you're programming in Java, that's what you're going to have to do. You have to get accustomed to knowing how to handle interrupts, which is why I wanted to cover this section. And you'll see in the current assignment, there's a bunch of places you have to check for the interrupts. And this is why you have to do that. OK, so that is the end of the section. So the last part, as is always the case, we try to give an example that's a bit more comprehensive. And this is a class or an application example called GCD Interrupted, the GCD Interrupted program. And what we're going to do is we're going to compute the GCD of two numbers. We've talked about this many times before. And the main thing that's different about this version versus the one we saw before was that the user can interrupt the program at any point. And if you interrupt it, then you get this little toast popping up saying that you've interrupted it. All right, so here's what it looks like. Here's the design. We've got the lifecycle logging activity, which just does some logging. We have the main activity, which is going to go ahead and start the computations and do the processing. And we have a GCD runnable, which is going to actually do the computations. And that's the thing that's going to check to see whether it needs to be interrupted or not. And let's see if we can go ahead and show this code. Let me go back and find where it is. So here's the code we're going to look at. I'll first show you the GCD runnable class, which, as you can see, implements runnable and extends random. It's got some fields that give a back reference to the main activity, the number of times to iterate. Those are set by the constructor. Here's the compute GCD method. No surprise, it's just a classic Euclid's algorithm to do this recursively. Here is the run method. Keep in mind that computing GCD is a classic compute-bound operation. There's no blocking going on there. We're not going to have to sleep. We're not going to have to block. We're not going to wait for locks. We're just going to do our thing. And because of that, we therefore have to explicitly check to see if we've been interrupted. And so what we do is we're going to run from I equals 0 to I less than the max number of iterations, which could be very large, just to make the program interesting. We'll generate 2 random integers. And then the next thing we're going to do is we're going to go ahead and check to see if we've been interrupted. And if we have, we're going to go ahead and log the fact we've been interrupted, and we're going to break. So we're done. Now, a design thing to consider at this point is, do we want to check whether we've been interrupted every single time through the loop? And the answer is probably not. So that would be incredibly responsive. We would be interrupted. We would detect the interruption the moment it occurs, but that's probably overkill. So it might be better to do something kind of like what I'm showing down here for printing the results. So what I do here is I only print the results, say, 10% of the time. So if I'm going to iterate for 1 million operations, I don't want to print 1 million values. I'm just going to print every, say, every 100,000 times I'll print something. So maybe it'll print much less. So I can do the same kind of thing for checking. I don't have to check every single time. Calling thread.interrupted is not a hugely expensive operation, but it's more expensive than checking a flag to see whether or not I should test whether it's been interrupted. So you might want to kind of optimize this out a little bit by not checking. Obviously, that's a trade-off between responsiveness and efficiency, and you have to decide for any given program what the right behavior is. So that was the runnable. Here's the main program. I'm not going to go through this in gory detail. It's mostly a bunch of Android code. Here's the default number of iterations. As you can see here, I think it iterates for 100 million times by default. That's quite a lot. Let's go down and take a look. Like I said, this is all Android code primarily. What we're going to do here is there's a method called start or stop computations. So the first time it's called, it's going to go ahead and start the computations. As you can see here, it takes the count that the user gave, which might have a default value. Once the thing is running, if you click that button again, and the thread has been allocated and is doing its thing, the second time you click this floating action button, which converts itself to a little X to indicate cancel, it'll then go ahead and interrupt the computations. So the first time it launches the thread and starts it, second time it cancels it. Here's what start computations does. As you can see, it makes a new GCD runnable, makes a new thread to run that new GCD runnable, starts the thread, and then it tells the floating action button, or the fab, to display the stop icon to indicate if you click the button, it'll shut down the thread. And then here is the interrupt computations method. That's what gets called back once we're up and running and we want to cancel it. It's very simple. As you can see here, we simply say mthread.interrupt. We set mthread up here when we made the new thread and started it. Down here, we interrupt it, and then we pop up a toast and say, hey, you've interrupted this thread. And we indicate what thread ID, thread information, is the thread that we're interrupting. So that's basically just a real quick example that shows how this works. And if you're curious, you can download it and play around with it. So that's basically the end of this example. This example illustrates that you can use thread cancellation with code in Android environment, just like you could do in a normal Java runtime environment, and it has much the same effect that you would be using. In fact, if you were using Android features such as async tasks, they have cancellation mechanisms built into them, and under the hood, the cancellation mechanisms of the async tasks simply use the Java thread interrupt mechanism that we just talked about.